So welcome again to another video. In this example, we'll be doing the electrostatic force. Right, so we are given this particular problem. We are told that there's a 4 microcoulomb charge placed at the origin, right? And then we have another 2 microcoulomb charge placed at x is equals to 0.3, positive 0.3. And then we have another minus 3 microcoulomb charge placed at x is equal to minus 0.4. Right, so check this. What you can do, okay, we're required to find the net force on the 4 microcoulomb charge. Let's do this. To make things easy, let's call this Q1, this Q2, and this one Q3. Right, so now let's sort of sketch what we're given here. If we imagine a Cartesian plane, imagine you have a Cartesian plane. Remember, Cartesian plane has the origin. So I'm using dots because I don't want to make this sketch messy if I use solid lines for the Cartesian plane. So imagine this is the horizontal x-axis, and then the vertical y-axis is somewhere here. Right, let's just put it like this. It's an imaginary. Right. So what ends up happening is we are told that the 4 microcoulomb charge is in the origin, or is on the origin, right? And then to the right of that, which is the positive side of the x-axis, we have another charge placed here. And then we have another one to the left, which is the negative side, placed there. Right. So from here, we can see that from this, we call this Q3 is which one? Oh, it's the minus one, Q3. Let's call this one Q1, which is this one. Then the one at the origin, right? Then we call the one to the positive side of the x-axis Q2, which is what we did here, right? So this is what we have. And then now you have 0.4 meters. We don't care about the negative sign. We just care about the distance. Distance is absolute. So it's an absolute value. It doesn't have a minus or a positive. It doesn't matter, right? Same as this side. Remember, if it's on the x-axis and I'm measuring it from the origin, I take the exact value as my distance. So this is 0.3. Right. If, however, maybe it was not on the origin, it was somewhere here, I would have to subtract to sort of find what distance that is. But in this case, it's from the origin. So I'm starting calculating, or I start counting from 0. So I know that if I start counting from 0, if I count from 0 to 5, it means the distance is just 5. If, however, I start counting from 2 to 5, it means the distance is 3. Right. Same thing we just did here. We were counting from 0 to minus 3. To minus 0.4. Therefore, we took the distance as just 0.4 meters. And then on the right-hand side, we were counting from 0, which is the origin, to plus 0.3 meters. And we definitely took the distance as 0.3 meters. That's all there is to it, right? So this is what the schematic looks like. So we're given this. Right. So now we are told to calculate the net force on the plus 4 microcoulomb charge, which is Q1, right? We called it Q1 in our case. We could have called it anything. The order doesn't matter. Q3 could have been Q1, Q2 could have been Q3, doesn't matter really. I just did it like this. You can make it however. So what we know is Q1 will feel a force due to Q2. And Q1 will also feel a force due to Q3. So we want to know what is the net force that Q1 will feel as a result of the presence of Q3 and Q2. That's what this question is asking us. So what we first do, we say, what is the force felt? Excuse me. So we say, what is the force felt by Q1 force on Q1, right? It is felt by Q1, but it is due to the presence of Q2. Let's start there. That's what it means when you calculate force using Q1, Q2. That's what it means. So let's call this force F1 for argument's sake. So you can say F1 is K Q1 Q2, Coulomb's law. All this over R squared, the distance between Q1 and Q2. So let's substitute. We said Q1 is 4 microcoulombs, so 4 times 10 to the power minus 6. Remember to always convert. We said Q2 is plus 2 microcoulombs. Remember, when you calculate the force, you don't need to put the sign for the charges. You use the magnitudes only, just absolute values. And then R squared is, R, the distance between Q1 and Q2, is simply 0.3 meters. So I get an answer of 0.8 newtons. Now remember, force is a vector, so I need to understand in which direction is this F1 going to. Of course, it's important to understand from what are you viewing F1, from which point of view, if I can call it. What's your reference? So let's get to that quick. So if we have Q1 and Q2, right, we will have something like this. Let me draw them. Right, so if we have Q1 and Q2, let's say this is Q1, this is Q2. These things are both, these charges, sorry, they are both positive. We have 4 microcoulombs, and this one is plus 2 microcoulombs. Remember, we said like charges repel. So Q1 will feel a force forcing it to go that way. We called it F1. So will Q2. So the force will be the same. The force felt by Q1 will be the same force felt by Q2. No, it won't be F2, it's just F1. Right, so they will feel the same force, which is what we just calculated here. So we are mostly interested in Q1 because that's where we want the net force. So where is the force on Q1 going? It's going to the left according to our diagram. So therefore we can say left. Right, so now we can find the force on Q1 again, but now due to Q3. So let's see if we can find the force on Q1 due to Q3. So let's call this one F2. And then F2, let's say we want to show the same thing in terms of the free body or something like that. Right, so we have this. And now we have Q3 and Q1, right? Say this is Q3, this is Q1. Q1 is plus 4 microcoulombs, while Q3 is minus 3 microcoulombs. So you see, these ones, they are not like charges, they are unlike charges. So we're expecting attraction. So that being said, we will have attraction rather than repulsion. So we'll have Q3 wanting to go that side, and we call this F2. The same force of attraction, they will feel the same force. I know my arrows make it look like the forces are different, but I'm telling you the force is the same. Right, just take my word for it. It's actually the same force. I just couldn't draw them to be the same length, the arrows. Right, so let's now calculate this force F2. Right, so we're finding F2 now. We said F2 is, you can call it F3, it's up to you, or F, I don't know, whatever number. So we have K, we still have Q1, but now we have Q3 instead of Q2. Okay, that doesn't look like a Q3. Let me just change it. That's a Q3. And then over R squared. Okay, my pen is misbehaving. So now we sub in our values. Remember, we never substitute the signs for the charges, only absolute values. You take them as positive even if it's negative, but only when you're calculating the force, right, and the electric field. Now let's find our R. We said is 0.4, right? What do we get as our answer? We find 0.675 newtons. But where is it going? Remember, we are concerned with Q1, and Q1 is going to the left. When you check the force on Q1, it's attracting to the left. Right, so that's what we have for now. And then we want to find the net force, right? So when we're finding the net force, we have to add F1 and F2, right? Remember, these are vectors, so choosing a direction is important. But before we get there, we were tasked with finding F net, which is F1 plus F2. So we choose left or right as positive, right? Let's say we choose right as positive, right? So let's say we choose right as positive. We'll say right is positive, right? That means our F net will be, where is F1 going? F1 is going to the left, so we'll put it as negative 0.8 newtons plus, where is F2 going? It's also going to the left. We put it as minus 0.675. Right. If it was going to the right, we were going to put it as positive 0.675. But now it's going to the left, which is opposite the direction we chose as positive. And then our answer would be 1 minus 1.48 newtons. What does this mean? It means since we chose right as positive, since our final answer is negative, it means it's opposite the direction that we chose as positive. So therefore, this is 1.48. Okay, my pen is doing funny things. Newtons where to the left because it's negative. Right, so that's where our net force is going. So this is how you would do a question like this one. Yes, thank you very much. See you on our next video.